Okay, I guess I can start. Can you hear me?
Yes, sir.
Yes, sir.
Okay. I'm audible. Okay. So yesterday I ended up in Lipschitz condition. Okay. So I told you that the existence and uniqueness theorem, it can be made stronger by making the condition weaker. Okay, so basically what we did, instead of Fy being continuous, in that rectangle, what we did, we showed that. In fact, we didn't show yet, but we had a couple of examples in that, like even when the Lipschitz condition is satisfied, we'll be able to prove uniqueness and existence. That is what it is, right? Although we didn't show actually by specifically mentioning Lipschitz condition, but when I proved the Picard's uniqueness and existence theorem, you must have seen that. In fact, we have already used this Lipschitz condition. Okay. So, and again, what Lipschitz condition is going to do, it is going to allow you to extend the interval of the solution to a bigger interval. Okay, not necessarily to a bigger interval, but it is going to extend the original rectangle that we had defined earlier, and you'll be able to see that later on. I'm going to do proof of this uniqueness and existence theorem, where the Lipschitz condition is going to be obtained. You will see that even a region which is not bounded, like say if we take an infinite string where the extension of the y-axis from negative infinity to infinity, even then it is going to work there. Okay, so that's what we are going to do. So now let me just take a couple of minutes to show you the formal definition of Lipschitz condition. So you can see in the slide that here one thing I would like to tell you is that here they are considering the rectangle to be your I cross S, where I is an interval in the real line, where they have considered S to be Rn. So you don't need to worry about it. What we are going to do, we are simply going to consider n equal to 1 in all the proofs that we have done. So this is the formal definition. You already are aware of that. You are already aware of that. So, and again, as you know, that constant k, it is called the Lipschitz constant. Okay. So basically, we will be interested in the cases where n equal to 1. Okay. So now let us try to work out a simple example, and after that, I'll be moving to the statement of Peano's theorem, which is part of your syllabus. But you will see that we have already done this. Okay, so you don't need to worry about it. So I'll do an exercise here. Okay, and example 2 here. It is very straightforward. You can easily do that. I think you can see that here. You'll be able to find out the Lipschitz constant to be, I think, 2AB. Here, the Lipschitz condition will come out to be 2AB. And just a minute. I will here, don't worry. In the here in the example 2, your case should come as 2AB. Okay, so now let me come to example 3, where you have been asked whether the function Fn x squared y Okay, fine. So, okay, so let us try to do this one because this is an interesting one. This is an interesting one. Okay, so we know that if we have to prove that this function is Lipschitz, this function is Lipschitz in some region belonging to R2, right? Then we must be able to prove that your f of your xy1 minus f of xy2 divided by your y1 minus y2. This is less than or equal to some positive constant k, right? Where k is called the Lipschitz constant. Okay. Now here you must remember is that this function I will be able to define only when both x and y they are going to bear the same sign. Okay, so that means if I consider your R2, then either both x and y they have to lie either here or here. Is it okay? Fine. So that means I have been able to close down on the possible reasons on which the function is going to be Lipschitz, if at all it is going to be Lipschitz. Is it okay? Fine. So now let us try to find this out. Okay. See, this is equal to your, and of course this is your ln x by y1 and x by y2, and eventually this is going to give me ln y2 by y1, right? Is it okay?
Yes, sir.
It's okay, right? Okay, fine. So now let us try to work out one thing. Okay, fine. Say you know that like say your ln y2 by y1 mod of ln y2 by y1 that is equal to mod of ln y1 by y2. Is it okay?
Yes.
Yes,
Fine.
sir.
Yes, sir.
Fine. And eventually, this I can write as what? Isn't it? I can write it as
Yes.
minus 1 into that, right? Isn't it? Fine. So
Yes.
for this particular term, okay, within this modulus sign, whether we keep y2 in the numerator or y1 in the numerator, it doesn't matter. Is it okay? Fine. Is it okay?
Yes, sir.
Fine.
Yes,
So
sir.
that means whether we keep y2 greater than y1 or y1 greater than y2, it is not going to matter. Is it okay? Fine. In finding out the value of both, log, y1 by y2 or y2 by y1, they are going to give you the same value, isn't it? Fine. So that is why let us assume that your y2 is strictly greater than y1. Okay. And I'll tell you why I'm not taking y1 equal to y2. That possibility. Say suppose for the Lipschitz condition, why I have to do this again. Your log question. See, if you take y1 equal to y2, if you take y1 equal to y2, then for this inequality to happen, for your this inequality to happen, say your ln y2 by y1 less than equal to a y1 minus y2 less than equal to y1 minus y2. So you will see that if you plug in y1 equal to y2, right? This is going to be the equality sign is going to make both the sides 0, isn't it? Right? So it is trivially satisfied. Is it okay?
Yes, sir.
Right? So that is why I am not really concerned about this being greater than equal. Okay, so I am going to concentrate only on strictly greater than. Okay, fine. And again, let me tell you, let me repeat it over and again. See, all this stuff that I have been telling you, once you go back home, you should write down everything systematically. Otherwise, you are going to forget it. Okay, fine. So now, suppose I take y2 to be greater than y1. So then what is going to happen? What is going to happen? This one, I can simply write it as ln y2 by y1. Fine? ln y2 by y1. Because this is always going to give me something greater than 1. y2 by y1. Is it okay? Fine?
Yes, sir.
Isn't
Yes,
it?
sir.
And in the denominator, I can simply write it this. Okay? Fine? So now, let us see. Okay. So now you know that. I mean, ln is something like 1 plus p. This is less than equal to p. Yes?
Yes, sir.
Right? It is less than equal to p. So now what I can do, this one, I can write as ln 1 plus fine. Okay, and so this will be less than equal to, so my p is this, right? My p is this, isn't it? Fine. So this is going to be less than equal to y2 by y1 minus y2 minus y1, and eventually you will see that you are going to get simply 1 by y1. Fine. Isn't it?
Yes, sir.
Yes,
Yes,
Fine.
sir.
Fine. So for the original function f to be Lipschitz, what I must have? I must have this is less than equal to some positive number k, isn't it? Some positive real number k, right? So that means what must happen? What must happen here? Obviously, y1 cannot be equal to 0. That is one thing. Fine. And what about the other thing? Can y1 be negative? Can y1 be negative?
No, sir. This was the first condition when it was inside log.
no, sir.
This was what? No, I say that they have to remain in the either both x and y has to be negative or both x and y has to be positive, right? But now I have this situation. Can y1 be negative? My point is that. Hmm?
Sir, y1 greater equals to 1 by k.
Less than equal to 1 by k. Less than equal to k.
One.
Yes.
Y1 greater equals to 1 by k. Here we get 1 by 1 y1 less or equals to k. Then y1 greater equals to 1 by k.
Okay, let me write it down. You said just give me. So you are saying that now y1 is greater than. Yes, you are getting to the point. Yes, fine.
And k is
If it is
positive.
negative, because k being a positive integer, that is going to be violated. Is it okay?
Yes.
Has everybody got the point? Fine, right?
Sir,
So,
sir,
yes.
y by y 1 by y1 less than or equal to k.
Okay, yes.
That implies y1 greater than or equal to 1 by k if y1 is positive. We already assumed that y1 is positive. Otherwise, if y1 is negative, then sign will be changed.
Did we assume y1 is positive? We didn't assume.
How can I get? Suppose I not assume that y1 is positive.
Okay.
Then how can I get y by 1 by y1 less than or equal to k implies y1 greater than or equal to 1 by k?
No, that is what I am asking. Can you do that? Can you say now? Can you tell me even when y1 is like say even when y1 is negative, still that inequality is going to hold? Because say anyway for any negative number it is always going to be less than equal to some positive number, isn't it?
Yes, sir.
Now you tell me. I mean. Why? I mean, I'm telling you the answer is going to be y1 will be positive, but you have to tell me why y1 is positive. I don't think I assume that. I mean, y1 is negative. Sorry, y1 is positive. I didn't assume at the very beginning. You think it, whether you can bring some something from its relation with x, the originally defined function, whether you can bring something from here or not, you tell me. And let me tell you is that the function is going to be Lipschitz only in the first quadrant. Okay, you think about it. Why? I mean, it is going to remain in the first quadrant. Okay, obviously, I'm not going to ask it in the quiz. Don't worry. So, have you received my email? Today, I have sent an email regarding your quiz 1.
Yes, sir.
Yes, sir.
Okay. So, what I'm going to do, I'm going to like submit it as assignment 1. Although, I mean, I have uploaded in my personal website the assignment, but it is going to be like say I'm going to upload on the day of the exam. The timing is from 12 to 1 p.m. 19th September. So I'm going to upload it probably 10 minutes prior to that, and then you answer the questions, write in a white sheet of paper, and neat and clean, and then you just scan it. It can be a JPEG file or PDF. I would have preferred PDF, but JPEG also it is fine. So then you immediately upload. Once you go to the Teams app for this course, you will see assignments and you will see your name, and then you can upload your assignment. Okay, but it has to, you have to upload it before 1 p.m. Remember. Sorry, I think I have given 1:10 p.m. or something like that. Okay, after that the deadline is gone. You won't be able to do it, and after that, you please don't request me. Okay, fine. So please bear all this in mind. Fine, and the syllabus is going to be whatever we covered till today's class. And again, let me just quickly just answer. So somebody asked me yesterday, like, here initially I was taking something like, say, okay, suppose this point was x naught plus a, this is x naught minus a. So the question was, I mean, like, when I am going to take a as h, so definitely a is going to be minimum of these two. One thing you have to remember, like say that slope of the tangent, the slope of the tangent, it could be 1, okay, less than 1 or greater than 1, right? So this situation where h is going to be exactly equal to a, that is going to arise when the slope is going to be very small. Okay, fine. Slope is going to be very small, because if it is less than 1, then assuming that assuming that m is a big number, right? Assuming that m is a big number, so something less than 1 here, it is going to make this even a bigger number, right? So there is every likelihood that, so this number will come out to be, I mean, the larger amongst these two, isn't it? Right? And if you have checked that thing, M1, if you have checked M1, that condition that I have imposed yesterday, so you will see that all the curves, they are always going to come below here. Okay, you check that. You simply think that, see, sorry, just a minute. Yeah, what is going to happen? What is going to happen? Sorry, not M, sorry. I'm getting it wrong. See, sorry, B by M. Sorry, B by M. Okay, so now if M is a very small number, this is going to be large. Okay, then if you have to choose between these two, definitely you are going to choose A. Okay, fine. So if M is smaller, there is every likelihood that all the curves are going to lie below this. Okay, fine. And if you consider this line to be, suppose you consider this line to be where your M equal to 1. The slope is 1. So obviously, I mean, a bigger slope is going to render all the curves to lie above this. Okay, so that is why in this case I have to reduce this interval. Okay, fine. So now let us try to prove. Your and before that, let me tell you something more. So now here you can see that it is talking about this Piano's theorem. Okay, so let me tell you, if the Piano's theorem is nothing but, it is only an existence theorem. Okay, Piano's theorem is nothing but an existence theorem. It doesn't take into account that continuity criteria for the first order partial derivative, or for that matter, any Lipschitz condition. Okay, so it simply says about the existence of a solution. That's it. Okay, and this is, I mean, named after Cauchy and Piano both. So this is the theorem. Okay, and here in this particular theorem, you can see that they have taken that interval. They have taken the interval to be this one, minimum of this A and B by M, and of course M is nothing but it is the bound of what? That slope function. Okay, fine. So now let us try to prove this. Let us try to prove theorem B. Okay, so theorem A, if you recall, theorem A was Picard's uniqueness and existence theorem, and over there, they were talking about a very small interval. Okay, now here you can see that they are talking not about a small interval. Here you can see that in the infinite strip, You can take any initial point x0, y0 in the infinite street, or maybe you can call it semi-infinite because it is extending infinitely on the L of y direction. Okay, so basically what it is saying, see earlier. So this is my initial zero problem. Okay, and we are assuming that this Lipschitz condition is satisfied. This Lipschitz condition is satisfied where I mean that R now it has been defined as xy belonging to R2 such that your x, just a minute here, okay, something like this, okay, and y is this, okay. Then this initial value problem, it possesses a unique solution for any x0, y0 belonging to this part. Okay, remember earlier we sought solution only in a very small interval in the neighborhood of this point x0. Okay, so what is the difference here? Like, what is the difference here? Can you tell me?
In previous it is symmetric interval.
Okay, fine.
But
Yes.
Here
Here it is not necessarily. Here, I mean, it has given me a possibility of getting a solution in a bigger interval, to be precise. Okay, so earlier it was absolutely local. So that is why the Picard theorem is also called local uniqueness and existence theorem. Okay, fine. So now let us try to prove it. So the strategy is going to be slightly different. And again, see here, the same sequence will remain. Okay, I'm going to define a sequence, but like I said, I'm not going to define a lot of stuff because we have already done it. Okay, so here what I'm going to just let me sorry, excuse me. Okay. Fine. So what we are going to do here, as before, again, I'm going to consider this sequence. You know what this sequence is. Okay, it is exactly the way we have done it in solving Picard's uniqueness and existence theorem. Okay, and here, once we have defined this sequence, after that we are going to define three. Say, suppose this is it, and then your for the next term in the sequence, let us assume that this is equal to m1, and then let us assume that your m equal to m naught plus m1. Okay, fine. And what we are going to do now, we are going to prove that this sequence is convergent. Okay, so we are firstly going to prove that this sequence is convergent, and then we are going to prove that the solution of the given equation is unique. Okay, fine. So how we are going to prove it? This is going to be slightly different. So here, so now your mod of this is definitely going to be why not? So this is equal to m1 plus m0. So that is why eventually I am getting this to be less than equal to n. Okay, so as before, what we are going to do, we are going to concentrate on the nth partial sum. If you have forgotten, so basically what we are going to do, we are interested in these terms, isn't it? Is it okay with everybody? We are interested in those terms, isn't it? Yes or no?
Yes, sir.
Yes. Okay.
Yes, sir.
So first two terms are already done. So definitely, even for this term also, I can write it as less than equal to m. Because see m0 is definitely less than equal to m. Is it okay? And for this, I have already found out that this is less than equal to m. Okay. So now, okay, let me proceed and then I'll tell you. So next we have to find out your y2x. So here it is going to be slightly different. Okay, I'm going to tell you what it is. X not x, so it is going to be f t y1 t minus f t y0 t. Fine. This dt. So here, what we are going to do, so we are going to make use of this. T, y0 t, then dt. And now from here, from here, what we get, see your, okay, let me just try to reduce this. Okay, so if I want to write down the term inside the modulus sign, so then you know that that is simply del f del y, right? And some t, some y star t, right? And then your y1 t minus y0 t, right? Is it okay? Fine. Y0 t. I'm going to get this, isn't it? Fine. So you already know that mod of this, if I have been assuming the same way as I did in proving Picard's existence theorem. So this was less than equal to what? K. Right?
Yes, sir.
Yes. So what we are going to get, so this is going to be less than this, and then this step is important. This step is important because this is y1 t minus this step is important. Okay, this is what it is. Okay, fine. So far so good. But here we have already assumed that y1x minus y0 it is less than equal to m, right? So for this what I can do, I can write this is less than equal to kn x0 x dt. Okay, and this is going to give me, this is equal to Km, you're simply x minus x naught, fine? Okay?
Yes, sir. Yes, sir.
Yes, fine. Now, so similarly, so now concentrate here. See, this relation gave me this. You simply concentrate on this. You simply concentrate on this. Say, suppose I simply fine. Okay. This gave me this relation. Okay. So that means what I got here eventually from here I too got this. Okay. Eventually this was ultimately fine. Okay. So now if I use the same thing for y3, y2, this would have given me here y2, y1. Isn't it? Is it okay?
Yes, sir.
Yes, sir.
Eventually we have got that. But from this relation, this is going to be simply your less than equal to Km t minus x naught. Is it okay? Isn't it? If I use this one, fine? Isn't it? If I use this relation, then this is going to give me, this is simply going to be less than equal to Km instead of x, it is going to be t minus x naught. Is it okay with everybody?
Yes, sir.
Yes. So
Yes.
that is why from here, that is why from this relation, I can simply write, see, this is going to be less than equal to K, then again Km here x naught to x t minus x naught dt. Is it okay with everybody now? Okay? Fine? This
Yes, sir.
is fine? Okay. So that means this is going to be equal to K square m, it is x minus x naught squared by 2. Okay? And I am going to write it as simple factorial because if you continue this process, say if you do it for y4 minus y3, it is going to lead you to k cube m x minus x naught whole cube divided by factorial 3. Is it okay? So this way we are going to proceed. Fine?
Yes, sir.
Yes? Okay. So that means what is going to happen? For the general term, I am going to have your y and x minus y n minus 1x. This is going to be less than equal to k to the power n minus 1 m, then x minus x naught whole to the power n minus 1 by factorial n minus 1. That's it. Okay, fine. So now one thing now just I want to tell you one thing. Earlier in Picard's theorem, what was happening? See that interval where we were trying to prove that the solution exists and it is unique. It was hovering around the point x naught, isn't it? Is it okay? Earlier, if you recall, this is where I was seeking my unique solution in Picard's theorem. Okay, fine. Now the difference is I am seeking a solution in the whole interval AB. Is it okay? Fine.
Yes, sir.
Yes. So that is why I have to be worried about my location of x naught, or for that matter my location of x. Okay, so obviously what is happening? Say suppose this is A, this is B. Okay, x naught is also fixed, it is somewhere here. Okay, fine. So now the x that I have chosen here, either it is going to be on the right of x naught, or it is going to be on left of x naught. Is it okay? Fine. Is it okay with everybody?
Yes, sir.
Yes. So then what is going to happen? If you look at this relation, let me call it A, what is going to happen? If I choose that, if your x lies between your x naught and B, x naught on B, so then what I am going to get, I am going to get from A your yn x minus yn minus x, it will be strictly, it will be less than equal to k n minus 1 and I don't have to adjust, this one. I don't have to adjust this one. Okay, because I know that this is already positive. Fine. Is it okay? This is positive. Okay, and then this is positive, and then what is going to happen? I can simply write it as something like this. Isn't it? Fine. See, for this interval, I absolutely have no problem. Okay. See, why I have to discuss it separately. If you recall, in Picard's theorem, earlier, this integration I was performing under the modulus sign. Now I am not doing that. Is it okay? Yes. So this is why this is why this question has arisen. Okay, fine. So now this is fine. I don't have any like say qualm about it. This is very good, because if x lies here, I mean I don't have it. Okay. So now what happens if x, say suppose x lies between a and x naught, right? So then what is going to happen? This is going to be your x minus x naught. That is going to be negative, right? So then what we can do? Then we can simply make use of this thing. Right? We can simply, what we can say, or even if we don't do that, I can simply say that this one would be just a minute. Let us not rope in here. So originally I can simply retain the modulus sign, right? And then from there I am going to arrive at this. And eventually whatever happens, because this is under the modulus sign, okay, this is going to be obviously mod of x minus x naught, that is going to be less than equal to b minus a. Anyway, is it okay?
Yes,
Fine?
sir.
Fine. So what we can say that in either case, I am always going to get this relation. Okay. So then Now let us come to the series. Let us come to the infinite series. Okay, so now if I come to this infinite series, anyway, so this is less than m equal to m. This was less than equal to m, and for this is simply going to be plus km b minus a, then k square m b minus a square factorial 2 somewhere here b minus a factorial n minus 1, this something like this. Okay, so basically so this is going to be this, and then this is what is this series?
To the power k into b minus
8, right? So e to the power k is b minus 8. So obviously this is m plus m e to the power k, right? Obviously this interval, the b minus a is bounded, k is also bounded, right? So convergence is true. Okay, fine. And again, as before, this convergence is going to be uniform convergence. Okay, so let me tell you, in many other books, while they try to prove uniqueness and existence theorem, what they do, they prove the stronger version. That is, what they do, they assuming Lipschitz condition, they prove it. And in most of the books, I have found that they use this concept of an infinite series, like this exponential function series. They use this. Okay, you will see once you look at covering school, you will see that they have been using this. Okay, fine. So let me move to the second part. Let me move to the second part. So what is that? What is that? See, first part, it has guaranteed me that a solution exists, right? It has guaranteed me that a solution exists, isn't it? Yes or no? Did I prove that this is a solution? I have simply proved the convergence, isn't it? Right? And if I assume that this sequence, of course, sorry, this is the sequence of functions. Remember, this is sequence of functions. So this sequence of functions is converges to the function y of x. We have already proved it in Picard's theorem that, like say, you can show that this is nothing but the solution of this equation. Yx equal to y naught plus x naught to x f dt. Is it okay? Fine. Isn't it? We proved it earlier. We don't need to prove it now because it is going to be the same, right? We have proved the convergence. Now that this is a, this limit is a solution to this equation. We call it 2. You can easily prove this. We have already done this. So it now remains to prove that this solution is unique. Okay. So what we are going to do in this particular case, we are going to assume that y tilde x is also a solution. Okay, y tilde x is the solution. So that means definitely it satisfies this equation. Definitely y tilde also satisfies this equation. So I can write it like this also. Say suppose this is 2 prime. 13. Okay, and then we will prove that the limit of this sequence is also y tilde x. Okay, because this sequence converges to a unique limit, isn't it? Fine. So that is why y tilde x and yx, they have to be the same. Is it okay what we are going to do? Fine. Today you guys have been very unresponsive. I don't know why.
Yes, sir.
Yes? Okay.
Yes, sir.
So here the strategy will be slightly different. It is going to be exactly like the way we prove the convergence of the sequence. So now, yes.
Here, how can we prove uniqueness?
That is what I am telling you, right? That is what I am telling you. That I am going to assume that y tilde x is also a solution. Right? I am assuming that y tilde x is also a solution of the original differential equation. So that means it has to be a solution of the relation 2, that your integral equation relation, right? So
Yes.
now, if how we are going to prove the uniqueness, I am going to prove that y tilde x is nothing but the limit of the original sequence, y and x, right?
Okay.
Y and x being uniformly convergent, it cannot have, I mean, 2 different limits, isn't it? Right?
Yes,
From
sir.
this. Okay. Right? So that is what we are. Here, just I mean, one example is simply like the way we define that M in the previous case. Oh, that's I hope I can get some machine to do the mopping. Okay, that's the time. Okay, anyway, this is the old method of chalk and talk. Okay, fine. See, you have to remember is that since I am going to prove it, that since I am going to prove this, so basically what I need, I simply need to prove that this tends to 0 as n tends to infinity. Fine, that is what we are going to do. So here we are going to assume that there is a positive number a such that a is nothing but the max of your y tilde x minus y naught, and for all x lying with a. Okay, fine. So now see what we are going to do. Simply, then we are going to find out this, then this, and so on. So this method of induction is going to lead me to a term for the left-hand side of this, and then from there we can easily. Okay, so that is what we are going to do. So since we so now let me be quick about it. You already know the definition. So from here, this is x naught to x f t y to the t minus what is going to happen, like f t y naught t, isn't it? Okay, fine. And as before, what is going to happen if I allow this t y to the t and as t y naught t? Okay, fine. So as before, what is going to come out? from here, using mean value theorem, firstly, what is going to come out? Like this. This is going to be less than k, and this one, your y tilde t minus y naught t. Fine? Is it okay?
Yes, sir.
Yes. So I can simply write it. I'm going to write it only once. Y tilde t minus y naught t and dt. Okay. So as before, like say now I have assumed that the a is nothing but the max of terms like this, isn't it? So from here I am going to get this is less than equal to km x naught dt, and this is going to be km your x minus x naught. Okay, fine. And then, as before, what is going to happen? As before, what is going to happen? Your just a minute, running out of charts. Your this y tilde x minus y2x, I can straightforwardly write from this step. I can straightforwardly write from this step that this is k x naught to x, and this is going to be y tilde t minus y1 t, right? dt. Okay, but I have already found out that y tilde x minus y1 x mod of that is less than this, isn't it? Fine. Simply concentrate on this and this. Okay, I have already found out that this is less than equal to that. Okay, fine. So here this is going to be less than k into km, and then integration x naught to x. This is x minus x naught, sorry, t minus x naught dt. Fine, and this is going to give me k square m. This is going to give me k square m x minus x naught squared by 2.
K square A, not M.
K
Yes,
square
sir.
what?
Not M.
Oh,
Capital A.
sorry. I am still in the earlier. Thank you. Here, just a minute. This is also A. This is also A. Okay, thank you. Fine. Okay, so now if I proceed in the similar way, you can easily see that what is going to happen. Your mod of y and x minus y tilde x, this is going to be less than equal to. Now see, this is say 2 n factorial n. Okay, I am going to get this. Fine. And again, I didn't tell you anything about where x lies. Fine. So as before, what we can do, whenever x lies, we can make this term to be less than equal to k to the power n a b minus a whole to the power n by factorial n. Is it okay? Fine. We'll give the same argument as before, right? So now from here, from this relation, if I call it say capital C, from here you can clearly see that if you let n tending to infinity, what you are going to get? You are going to get this sequence also converging to y tilde x. Okay, so what must happen? This solution must be unique. That's it. Okay, so this is about the proof of uniqueness and existence theorem using the Lipschitz condition. Okay, fine. So now I am going to go to a very interesting concept. Let me. Did I mention? Did I tell you about the locality? Just a minute. I just want to. Okay, fine. So this continuation of solution. Let me tell you that it has something to do with the local, uniqueness and existence theorem. So local uniqueness and existence theorem is nothing but your. I want to be more precise, like Picard's uniqueness and existence theorem, but over there, what we are going to do, we are going to apply that minimum of A, comma B by M concept. Okay, I'll see what. So, do you have any idea what is going to be there in continuation of solution? Yes, it has something to do with that local. Yes. Once I tell you about another term, I think then you will have the idea. Okay.
Sir, what is the question? Please tell again.
The next thing I am going to discuss is continuation of solution, not continuity of solution, continuation of solutions.
Yes, you want to extend the interval.
Yes, yes. So basically, like say the uniqueness and existence theorem, it provides, like say the local uniqueness and existence theorem, it provides me with a very small interval around the initial point, right? So now the question will be whether I can expand it and under what circumstances I will be able to expand it. Okay, so today, I mean the theorems I will do in my next class after maybe Monday. So today I'm going to finish with one particular example. Okay, so now what we are going to do, continuation of solutions, and then from here in fact maximal interval of definition or validity whatsoever. You know what it is. Okay, fine. So let me take this. Let me take this particular problem. Okay, fine. Now, what we can do here, like obviously, you know that this f of xy, this is simply x into y, and you know that this is continuous throughout the whole R2. Is it okay?
Yes, sir.
Yes, sir.
Fine. So, if we are seeking a solution in the neighborhood of the point 0, 1, right? So then that, okay, let us not use the word d, that rectangle where I am going to assume that both f and first order derivative of f with respect to y is continuous. I can choose it to be somewhere around this point, right? And let me call this as, it is simply what is going to happen such that your x minus 0, say less than equal to a, fine, and y minus 1 less than equal to b, right? Isn't it? In the original, right? Existence and uniqueness theorem, I can choose my rectangle R to be like this. Okay, fine. And what your existence and uniqueness theorem, it is going to guarantee me that I have a solution in the interval. I have a solution in the interval, say x0 minus h, x0 plus h, right? And here since x0 equal to 0, so basically this is minus hh, okay, where your h is given to be your minimum of your a, then b by n, right? Is it okay? Fine.
Yes,
And
sir.
of course, what was m? M was nothing but the bound of the function f of xy. So that means m is such that f of xy less than this. Okay, fine. So now let us try to find out the maximum value of f of xy, that is xy in this interval, like sorry, in this rectangle. Is it okay? Fine. Now, what I am going to do here, you see, and obviously, like this is simply, I mean, x into y. This is simply x into y. Okay, fine. So obviously, here, what is going to happen? The maximum of this, it is going to occur on the boundary of this, isn't it? Because first order partial derivatives of that is what? That is simply 0, 0. Fine? Isn't it? That is simply 0, 0.
Yes, sir.
Fine? And now, if you try to find out at the boundary, so then obviously for x, I am going to choose the right boundary A. Okay? From here. And for y range, you will see that y range is what? Y is less than or equal to what? 1 minus b, 1 plus b.
Yes.
Yes. So the max of this is going to be given by a into 1 plus b, because I am assuming that both a and b are strictly positive. Is it okay?
Yes, sir.
Yes.
Fine? Is it okay with everybody? I am
Yes.
seeking
Yes,
the
sir.
maximum value of the function x, right? So that is why a into b, a into 1 plus b. Okay, fine. Okay, fine. So far, so good. Let us see. See, this problem is very simple, but it is a very interesting example. I think you still don't have any clue where I am going ahead. Okay, fine. So now here, say suppose your say case one. Suppose your a is greater than 1. A is greater than 1. So obviously then your 1 by a is going to be less than 1. Okay, fine. And your b by 1 plus b, it is already less than 1, isn't it? Fine.
Yes, sir.
This is less than 1. Fine.
Yes, sir.
So this product, it must be eventually less than 1. Yes.
Yes, sir.
Fine. So that
Yes, sir.
means if a is greater than 1, the minimum of this is definitely going to be less than 1. Isn't it? Right?
Yes, sir. Yes, sir.
Yes.
Yes.
Fine. So now let us assume that this case 2, let us assume that a is less than 1. If a is less than 1, then definitely, I mean, 1 by a, I am assuming it to be, definitely it is going to be greater than 1. Okay, so now I don't know what is going to be the value of this. This may be greater than 1 or less than 1. But since we are choosing the minimum between these two, fine. So that is why in either case, H is always going to be strictly less than 1. Is it okay? Yes or no? Of course, I can use this also. Fine. Are you getting my point? Because A is already less than 1, we are going to choose the minimum between these two. Whatever may be the value of this, I know that this is a positive number, right? So the minimum of these two numbers is always going to be strictly less than 1. Is it okay with everybody?
Yes, sir.
Yes.
Yes, fine.
Yes, sir.
So that means in either case, we have found out that this mod of H is less than 1. Okay, fine, right? Is it okay with everybody? Right? So the local interval where a unique solution exists, it is going to be something like, it is going to be something like this, or even that interval is going to be smaller than this. Is it okay? Fine. Because I am seeking this interval minus h to h. Isn't it?
Yes, sir.
So basically, this is going to be a subset of this interval. Okay, fine. Can you solve the original differential equation for me? If you have forgotten the original differential equation first. Can you solve it for me? Yes, please. I'm tired. I have done a lot of things for you. Now, I'm begging you to do something for me. Has somebody found out the solution?
To the power x square by
Yes. Y equal to e to the power x square by 2. This is correct. Okay. Fine. Now, what is the interval of deformation of this?
minus infinity to infinity. Minus
infinity to infinity. Okay. Because anyway, you know that if you had found out, say, fy, right, that would have given you x, right? Okay, and x is continuous throughout the whole interval, minus infinity to infinity. Fine. So, although the uniqueness or existence theorem has given me a local interval, which is like, say, at most can be this. Fine. At most can be this. I can find a much bigger interval. Here, of course, it is going to be the maximal interval. That is going to be the largest interval, because the largest interval cannot go beyond negative infinity to positive infinity, right? Okay. So I can get a maximal interval where the solution is unique. So that is what we are going to do. So this is about continuation of solution. So basically, what is the meaning of this? See, in this particular case, sorry about this. Okay, see, in this particular case, what is happening? Oh, this is 0. So the uniqueness and existence theorem had landed me in this interval, whereas I had the opportunity to extend it to a much bigger interval. Okay, so this is what we are going to do. So whether I can continue beyond this right limit and the left limit so that I can get a bigger interval. Okay, so that is what we are going to do. I'm just going to prove one simple theorem, and I'm going to give you what is I mean, what are the possibilities of the extent of this maximal interval? Okay, right? And then I'm going to do it. Okay, so then I'm going to meet you on Saturday. So Saturday, what you do, I'll be there. I'll be there. So what I'm going to do, I'm going to switch on to our regular class schedule there. So you do what you think, whether you log in or not, it is up to you. So if you have any question, just you can ask me through here. Is it okay? Fine. So through Teams app, you can ask me questions. Of course, I'm not going to answer any questions regarding the quiz. I'm not going to give you the answer to the questions of the quiz. So if you have any doubt or something like that, you can tell. Okay. So I think I'm going to wind up my class here. Yeah.